The servers are running, security groups look fine, and an entire subnet just went dark. No inbound, no outbound. The instances are healthy, but talking into a void. One line and one routing table is the difference. Episode 8 of Cloud Architect Path starts now. By the end of this video, you'll be able to look at a network layout and know instantly whether a subnet is public or private, when to reach for an internet gateway versus a NAT gateway, and how to connect one VPC to another. This is the plumbing that every security, endpoint, and cost topic later in the course quietly depends on. For 7 episodes, we've focused on identity and data. Who can act, and how your data stays encrypted at rest and in transit. Now we shift to the network layer, the plumbing all of those resources actually stored inside. Think of this episode as a vocabulary primer. We're loading the core VPC terms so the deeper security, endpoint, and cost videos ahead have something solid to build on. Before we get into the mechanics, 5 terms are doing all the work in this episode. A VPC is your own logically isolated virtual network in Amazon Web Services, scoped to a single region. Nested inside that VPC, a subnet carves out a range of IP addresses and anchors itself to exactly one availability zone. A route table is the set of rules that decides where a subnet's outbound traffic is forwarded. Think of it as the network's decision engine. An internet gateway is the highly available component that carries traffic both into and out of the VPC for any resource holding a public IP. And a NAT gateway handles the inverse scenario. It lets instances in a private subnet reach out to the internet while blocking unsolicited connections from reaching back in. Here's Megacorp's problem. Their procurement services handle supplier data, so those servers must stay completely unreachable from the public internet. Nobody on the outside should ever be able to open a connection to them. But at the same time, those same servers still need to call Amazon Web Services APIs and pull down software updates. That's outbound access, so the requirement is oddly specific. Reach out, but never be reached. You can't design for that until you understand the plumbing underneath, so let's build it up piece by piece. The cleanest way to hold this hierarchy in your head is a building. A region is a city. A VPC is a single large office building in that city. Availability zones are separate floors of that building, physically isolated so that a flood on one floor doesn't sink the others. And a subnet is an individual room. Each room sits on exactly one floor. It never straddles 2. So a VPC fills the building. Floors are your availability zones, and every subnet is a room pinned to a single floor. That spatial picture gives you the 2 rules that trip people up most. Here are the 2 rules, and they're worth memorizing word for word. A VPC spans one region across all the availability zones inside that region. It cannot stretch to a second region, and a subnet lives in exactly one availability zone. It cannot span 2, so the building can't extend into another city, and no single room can sit on 2 floors at once. When a question implies a subnet somehow covers multiple zones, or a VPC reaches across regions on its own, that answer is wrong. That one zone rule isn't just trivia. It shapes every resilient design you'll build. Because a subnet is pinned to a single availability zone, that subnet cannot survive its zone going down. So high availability means duplicating your subnets across at least 2 zones. That's exactly why in resilient architectures, you see NAT gateways, load balancers, and databases deployed per zone rather than once. And because a VPC never spans regions, anytime you need to connect workloads in different regions, that always takes an extra mechanism. We'll get to those mechanisms shortly. Now the piece that quietly runs everything, the route table. A route table is just a set of rules deciding where a subnet's outbound traffic is sent. Every route table comes with one route you can never remove. called the local route. It covers the VPC's own address range. That local route is the reason any two subnets in the same VPC can talk to each other automatically, with zero setup. Internal connectivity is free and built-in. On top of that local route, you add more routes that send other destinations to specific targets. An internet gateway, a NAT gateway, or a connection to another VPC. Change those routes, and you change everything about what a subnet can reach. Picture the route table as the GPS in every car leaving a neighborhood. Give it the right map, and every trip reaches its destination without a hitch. But delete one road or point it at a dead end, and cars just drive off into nowhere. The engine still runs, the wheels still turn, but nothing arrives. That's the quiet danger of a route table. Everything looks perfectly healthy while traffic silently vanishes. Here's how the docs define the single most important distinction in this whole topic. If a subnet's route table has a route to an internet gateway, it's a public subnet. If that route table has no route to an internet gateway, it's a private subnet. Read that again because it's doing something subtle. Public versus private isn't a property of the subnet itself. It's decided entirely by whether the route table has that one route. So let's kill the number one misconception right now. There is no make public toggle on a subnet. You cannot flip a switch and declare a subnet public. Going back to our building, the subnet is a room and the route table is the directory of hallways. A room only becomes public if a hallway leads from it to the front door, the internet gateway. Paint that door any color you like. If no hallway connects to it, nobody gets in or out. The room's publicness lives in the hallway map, not in the room. So what is that front door exactly? On the left, we have a public subnet with a resource that holds a public IP address. That resource connects to the internet gateway, sitting in the middle. And notice the arrows run both ways. Traffic flows out to the internet, and traffic can also come back in. From the gateway, on the right, we reach the open internet. The important word here is two-way. An internet gateway allows both inbound and outbound. Visitors can walk in, and people can walk out. Hold on to that because the next component behaves completely differently. A few concrete facts about the internet gateway. It's horizontally scaled, redundant, and highly available. You don't size it, and you attach exactly one to a VPC. It enables that two-way traffic, but only for resources that actually hold a public IP address. For IP version 4, it also quietly does one-to-one network address translation, mapping a private address to a public one. And here's a detail people love. The gateway itself is free. Amazon Web Services charges nothing for the component. You only pay for the data transfer of the instances using it. Let's lock in what we have so far. A VPC is one region. A subnet is one zone, and neither stretches beyond that. The route table decides where a subnet's traffic goes, and it always carries that unremovable local route for internal chatter. A route to an internet gateway makes a subnet public, and no such route makes it private. And the internet gateway itself carries traffic both in and out, but only for resources with a public IP. That's the public side. Now let's solve Megacorp's actual puzzle. Back to Megacorp. Their procurement servers sit in private subnets, which by definition have no route to an internet gateway. That's exactly what they want, because it means the internet can never open a connection to those servers. So far, so secure. But remember the twist. Those servers still need to reach out, to call Amazon Web Services APIs and download patches. So the question becomes, how do you grant outbound access without ever granting inbound? A private subnet with an internet gateway route would break the whole security model. This is precisely the gap that network address translation fills. The documentation puts it in a single clean sentence. You use a NAT gateway so that instances in a private subnet can connect to services outside your VPC, but external services cannot initiate a connection with those instances. That's the entire idea. Outbound, yes. Inbound from strangers, never. It's the perfect fit for megacorp's requirement. Think of the NAT gateway as a one-way turnstile at the back of the building. Staff can step out to run errands whenever they need to, but the turnstile is built so that no stranger can push their way in from the outside. Compare that to the internet gateway, our two-way front door where visitors walk in freely. That contrast, two-way door versus one-way turnstile, is the heart of this whole lesson. Let's trace the full path. On the left is the private subnet with Megacorp's procurement server. Its route table sends internet-bound traffic, that default route to everywhere, over to the NAT gateway. And here's the detail people miss. That NAT gateway lives in a public subnet, not the private one. From there, the NAT gateway forwards the traffic onto the internet gateway, which finally reaches the open internet. Follow the arrows and they only point one direction. Outbound. There's no path back in. The server gets its updates and its API calls and stays completely unreachable from outside. This is the placement rule to burn into memory. The NAT gateway sits in a public subnet, the one with a route to the internet gateway. Then the private subnet's route table points its default route at that NAT gateway. If you ever see an answer that puts the NAT gateway inside a private subnet, reject it immediately. A NAT gateway in a private subnet has no path to the internet itself, so nothing downstream of it can get out. There are actually two ways to do NOT, and the exam wants you to know the difference. On the left is the NAT gateway, the managed option. Amazon Web Services runs it, patches it, and scales it for you automatically from 5 gigabits per second up to 100. There's no operating system and no failover to build. This is the default recommendation. On the right is the NAT instance, the do-it-yourself option. It's just an EC2 instance you own and manage. You pick the size, patch the operating system, disable its source and destination checks, and build your own failover. Its legacy at this point, surviving mainly as a narrow cost play for low-traffic, non-production environments. One more picture to make the trade-off stick. A NAT gateway is like taking a managed airport shuttle. Amazon Web Services drives, fuels, and maintains it, and swaps in a bigger bus automatically when the crowd grows. A NAT instance is renting a van and driving it yourself. It looks cheaper on paper, but you buy the fuel, do the oil changes, and if it breaks down at 2 in the morning, that's your problem. Cheaper is rarely free once you count the engineering time. The capacity numbers make the case on their own. A single NAT gateway starts at 5 gigabits per second of bandwidth and automatically scales all the way up to 100 gigabits per second. On packet rate, it begins at 1 million packets per second and climbs to 10 million, with zero configuration on your part. Now imagine hand managing a NAT instance to match that. You'd be juggling instance sizes and monitoring constantly. That elastic headroom, handed to you for free, is exactly why the managed gateway is the default answer. Here's a resilience detail that flows straight from our subnet rule. A NAT gateway lives in a single availability zone. So if you share one NAT gateway across multiple zones, you've built a blast radius. The moment that one zone fails, every other zone loses its outbound internet along with it. The resilient pattern is straightforward. Put a NAT gateway in each zone's public subnet. Then, each private subnet's route table points at the NAT gateway in its own zone. Now, a single zone failure only affects that zone, not the whole system. Now let's return to that opening mystery. When you see private instances can't reach the internet, the culprit is almost always the route table, not the NAT device itself. 3 failures caused the vast majority of these. First, the NAT gateway got placed in a private subnet, so it has no path out itself, and everything behind it breaks. Second, the private subnet is simply missing its default route to the NAT gateway. And third, the public and private subnets accidentally share a single route table. Amazon Web Services explicitly warns against this because it breaks the routing that NAT depends on. In all three cases, the servers are healthy. One route is wrong. And keep this contradiction sharp in your mind. A private subnet with a route to an internet gateway cannot exist. It's a contradiction in terms. The instant you add that route, the subnet becomes public by definition. So if an answer describes a private subnet that somehow routes directly to an internet gateway, you know it's wrong on its face. Private means outbound through NAT, never a direct internet gateway route. Quick recap on NAT before we connect VPCs together. NAT gives private subnets outbound-only internet with no unsolicited inbound. The NAT gateway itself goes in a public subnet, and the private subnet's route table points its default route at it. Prefer the managed gateway over a self-managed instance, and deploy one per zone for high availability. And when outbound breaks, look at the route table first, because that's nearly always where the fault lives. So far, we've stayed inside one VPC, but real organizations run many. How do you connect them? The first tool is VPC peering. The docs describe it as a networking connection between two VPCs that lets you route traffic between them using private addresses. Instances in either VPC can then communicate as if they're on the same network. No internet, no gateways, just a direct private link between two VPCs. Simple and clean, with one crucial catch. That catch is the single most tested fact about peering. It does not chain. If VPC A peers with B and B peers with C, that does not give A path to C. Peering is strictly point-to-point and non-transitive. Think of it like having each friend's personal phone number. To reach a friend of a friend, you still need their number directly. Introductions don't pass down the line. So every pair of VPCs that needs to talk requires its own dedicated peering connection. This picture shows why non-transitivity becomes a headache at scale. On the left, 5 VPCs connected by peering. Because every pair needs its own direct link, you end up with this tangle of connections crisscrossing everything. It feels fine with 3 or 4 VPCs, but the math is quadratic. 6 VPCs need 15 connections, and 12 VPCs need 66. On the right is the alternative. Every VPC attaches once to a central hub in the middle, and now any VPC can reach any other through that hub. 5 clean spokes instead of a messy web. That hub is the transit gateway. Here's what makes the transit gateway different, straight from the Amazon Web Services white paper. Transit gateway is a regional resource, and it can connect thousands of VPCs within the same region. The key word is transitive. Unlike peering, once VPCs attach to the hub, they can all reach each other through it. Picture a group conference call. Everyone dials into the one line, and now anyone on the call can talk to anyone else. One attachment per VPC replaces that entire mesh of point-to-point links. So which do you choose? The decision rule is clean. When a scenario involves just a few VPCs, or asks for the lowest cost between 2 specifically named VPCs, peering is the intended answer. But when the question stresses many VPCs, scaling, or reducing operational overhead, that points to transit gateway. Remember the quadratic growth. 6 VPCs already need 15 peering connections, and 12 need 66. And one shared fact about both, peering and transit gateway are each regional constructs. Neither spans regions on its own, which is why cross-region always takes an extra step. Let's carry the core rules forward. A VPC is one region across its zones, and a subnet is exactly one zone. Public versus private is decided entirely by the route table. by whether there's a route to an internet gateway. An internet gateway is two-way for public IP resources, while a NAT gateway is outbound only for private subnets. That NAT gateway goes in a public subnet, one per zone for high availability, and the managed gateway beats a self-managed instance. And to connect VPCs, peering is non-transitive and point-to-point, while transit gateway is the transitive hub for many VPCs. Now let's see how well all of that landed with a quick 5-question quiz. You now have the VPC vocabulary the rest of networking stands on. Coming up, we get into security groups and network access control lists, the tools that control traffic inside this plumbing. After that, VPC endpoints for reaching Amazon Web Services privately without ever touching the internet, and then the full networking cost picture. Each of those builds directly on the subnets, route tables, and gateways you just learned. Let's test what you've learned. An engineer creates a new subnet and wants it to be public. What actually makes a subnet public in a VPC? Is it A, its route table has a route to an internet gateway? B, enabling a public subnet setting when you create it? C, assigning the subnet a public address block? Or D, placing the subnet in the first availability zone of the region? Pause here if you want more time. The right call here is A. There is no make public switch on a subnet. A subnet is public purely because its route table carries a route to an internet gateway, and private when it doesn't. It's a routing decision, start to finish. Question 2. Instances in a private subnet need to download updates, but must never be reachable from the internet. Where must the NAT gateway be placed? A, in the same private subnet as the instances? B, directly on the internet gateway, replacing it? C, in a separate region connected by peering? Or D, in a public subnet with the private subnet's route table pointing its default route at it? Lock in your answer before I give it away. If you said D, well done. A NAT gateway needs its own path out, so it lives in a public subnet. Put it in a private subnet and it has no route to the internet itself, which breaks everything downstream of it. Question 3. VPC-A is peered with B and B is peered with C. Instances in A cannot reach instances in C. Why? A, peering connections expire after 1 hour. B, VPC peering is non-transitive, so A cannot reach C through B. C, A, and C share an availability zone, which blocks peering. Or D, the local route embrows the peering routes. Think about which rule matters most here. This one is B. Peering is point-to-point and non-transitive. A path through B does not carry over to C. You need a direct A to C peering or a transit gateway hub to make it transitive. Question 4. A company has grown to 12 VPCs that all need to talk to each other and wants to minimize operational overhead as it keeps adding more. Which approach fits best? A full mesh of peering connections between all 12. B, a NAT gateway in each VPC forwarding traffic. C, a transit gateway that all VPCs attach to as a central hub. Or D, an internet gateway shared across all 12. Got your pick? Let's see. It has to be C, and here's why. Many VPCs plus reduce operational overhead is the signal for transit gateway. A full mesh of 12 VPCs would need 66 peering connections. The hub replaces all of that with one attachment each. Last question. After a deployment, instances in a private subnet suddenly can't reach the internet, even though nothing about the instances changed. What's the most likely cause? A, the internet gateway silently switched to outbound-only mode. B, the instances lost their public addresses. C, a root table problem, like a missing route to the NAT gateway or a shared root table. Or D, the VPC automatically shrank to one availability zone. Run the decision rule from earlier before you answer. The answer is C. When private instances go dark, look at the route table first. It's nearly always a missing default route to the NAT gateway, a NAT in the wrong subnet, or the public and private subnets accidentally sharing one route table. The instances are fine. One route is wrong. You now have the VPC vocabulary the rest of networking stands on. Coming up, we get into security groups and network access control lists, the tools that control traffic inside this plumbing. After that, VPC endpoints for reaching Amazon Web Services privately without ever touching the internet, and then the full networking cost picture. Each of those builds directly on the subnets, route tables, and gateways you just learned.